Right, so you have learned about the theory of reliability, you learn about the background of the research, and what is the most important to you is how I could use them and design the power, right? So the following presentation is to show you a series of examples, selected examples, to show you a step-by-step procedure of designing the power using Iowa Blue Book, right? Checking and verifying the power performance in this example using a modified Iowa ENR formulas. Right? I will try to go slow on this example as this is the first example showing the LRTF design procedures. So what you will learn from this presentation is to able to follow the geotechnical design and the construction steps to implement the proposed LRTF design procedure using the modified Iowa DOT formulas as a construction control method. Select the right resistance factors from the table that I just showed you previously for design as well as for construction control. Right? And able to come up with a contract length that is required, as well as the target driving resistance that required during construction. Right? Design to determine contract length, as well as the target resistance required to verify the power performance during driving at the site. This example is an integrated abutment, a timber pile construction in a non-cohesive soil construction control using modified Iowa DOT formulas. Okay? So step one is to determine the situation plan, determine the layout, the length of the span. In this example is 120 feet, three-span continuous concrete slab with a 25-degree scale, integrate abutment shown on the diagram, and an amazing cut of the cross-section done by Don. And based on the bridge design manual, if the span length less than 130 feet, we do not require any pre-boreholes. Right? And elevation of 922. Step two is to come up a soil package. It's basically to determine the site investigation and recommend a foundation system for the bridge. So this is a soil profile. As you can see, you have 5 feet of soft to stiff silty clay, 20 feet of fine sand, 40 feet of medium sand, and below is a bouldery, gravel, and hard shell. Primary is a non-cohesive soil profile, but we will check that and verify that. And the soils design engineer will recommend and develop a foundation recommendations. In this example is a timber pile, tip out in medium sand, normal driving resistance, no significant down drag in non-cohesive materials, no special site consideration for stability, settlement, or lateral movement. Step 3 is to determine the number of piles and the arrangement of the piles in a pile cap. So the final design engineer come up with this recommendation, 12 numbers, it should be 12 numbers of timber piles based on the recommendation. Each timber pile will subject to a factor load of 54 kips per pile based on a strength limit state number 1 as specified in the ASTO specification that strength load combination number 1 is basically the dead load plus live load, right? Axial dead load and live load. And we want to know if that timber piles has that capacity to resist the structure load, and the driving resistance shall be equal to 0.9 that resistance factors applied to the structure capacity of the timber pile. The maximum allowable capacity of the timber is 64 kips That is, again, the same value that are given in the bridge design manual for timber pile. You come up with this number, 57.6. We say that this is greater than 54. We are good with the selection of the timber pile and the number of piles. So in this example, no uplift, no down drag or scour consideration. Construction control, again, remind, is to use the modified Iowa DOT formulas and no special consideration, especially the lateral load or down drag or scour in this example. Step 4. Step 4 is for those who are familiar with using the Iowa design chart to come up with the geotechnical pile resistance. Basically, this is step 4. It's the same thing, is to determine the nominal pile resistance. So we have few layers along the pile length. Right? The first layer is soft to stiff silty clay. Thickness is 5. The average N value at this layer is 4. And 1.4 is the number that you selected from the Iowa design chart. Right? Correspond to the N value, correspond to the type of soil that you have at this layer. Right? So it will be 1.4 kips per foot. And the cumulative for the first layer, the friction resistance at the bottom of this layer 1 is basically taking this 1.4 unit friction, multiply with the thickness 5, right, and give you 7 kips of friction for the layer number 1. Following? Right? Then you go to the second layer, which is a 5 sand. Right? 5 sand is 20 feet thick, and the average N value is 16. And if you refer to the Iowa design chart, correspond to this N value and the soil type, and the right unit friction should be 2.4 kips per foot. Right? So the numbers here, 55, is equal to, this is a cumulative, right, from the previous layers. So it's equal to 2.4 multiplied with 20. That gives you 40.8 kips plus the 7 kips from layer number 1. That a cumulative of 55 kips total up to layer 2. That is the cumulative geotechnical site friction so far up to layer 2. And you continue to the third layer. This should be 3 here. Medium sand layer, 40 feet, and the N value is 20, and you select the numbers from Iowa design chart, and this is the unit friction 2.8, and the cumulative of that numbers is equal to 2.8 multiplied with 40, plus the cumulative up to layer 255, and that gives you a total of site friction 167 kips. Any questions up to this point?
Yeah, your last slide, you said there's 2 piles.
Right. Okay. Just a correction here, should be 12 piles in a group. Any question up to this point? And of course, you do have an N bearing because the N value is 20 in sand, and you do have an N value of 32 kips. Right? So you have a total friction up to a depth of this layer of 167 plus the N bearing of 32 kips. Questions so far up to this point? Yes?
The chart shows the value of 3.2 for the fine sand, medium sand.
Medium sand, all right.
It shows a value of 3.2 in the chart. I don't know whether that's...
Can you?
Well, I mean, for an N value of 20.
That's for a root point, right? Something has some mistakes in what you had.
could be an error.
Yeah.
Yeah, it should be around 3.2 based on the design chart. Right? For medium sand, under wood pile, I must have selected under the steel pile.
Yeah.
Good point. So that number, 2.8, should be around 3.2 if it's based on the design chart. All right?
Interpolated that.
So, but again, sometimes it's subjective because the end value and the soil type may not exactly match what is given in the design chart. So judgment needs to be called at this point that, what will be the right number to choose. It happened to me when I'm analyzing the historical data. I'm debating what number should I use, especially when you have the borrowing from the given by the contractors, and the soil description is not what is given in the table. That could be a challenge to come up with the numbers. All right? Should I continue? All right? So now, step 5 is to determine and select the right numbers. Right? It could be difficult at this point because this is the first time you see a table overwhelmed with a lot of numbers. Right? Let's focus on what we actually specified early. We're saying that we're going to use the DOT ANR formulas as our construction control. Right? So all you need to know is what should I choose from the first row. Again, you refer to the soil type along the pile, mostly a sand. Right? So will be at this point that the resistance factors should be 0.5 under the non-cohesive column. Right? For design, using the blue book. Right? So the right resistance factors that select from this table is 0.5. Right? So step 5 again is you pick the right resistance factors from the table, and in this case is 0.5. And you want to determine the nominal geotechnical pile resistance. Right? If you recall back the limit state equations that we have on this paper, on this board, we have the factor load that's given to you. We have selected the resistance factors. All we need to find right now is the Rn, the nominal pile resistance. So what is showing here is the rearrangement of this equation. Basically, is to take these resistance factors and bring it to the left side of the equation. And with that, you have Rn on this side and the rest on this side. If you do have dow drag, you can include this component. The dow drag will contribute an additional load on the pile. Right? So the factor load given to you is 54 kips factor load, which is the load factors multiplied to the load. 54 kips plus 0, in this case is no dow drag, and divided by the phi factors that we just selected from the table, 0.5, and the calculated normal resistance is 108 kips per pound. That is your nominal geotechnical power resistance that you required. Okay? So next is step 7. We know that we require 108 kips. Right? But we want to know how far the power should be driven into the ground to get the 108 kips or more. Right? So this step basically is to go through the layers by layers and determine the contract length. Right? I will walk through this calculation slowly. So at the depth 0, no embedment, you have 0 resistance. And down to layer number 1, which is 5 feet of clay, the RNBB1 at layer 1, which is the nominal resistance based on the blue block, up to layer 1 is equal to the resistance from layer 0, in this case it's 0, plus the resistance contributed by the 5 feet clay. So you have the unit friction 1.4 multiplied with 5, which is 7 kips that we just calculate and shown on the table on the previous slides. Next is you continue to layer 2, right? Because you know that up to layer 1 you only have 7 kips, right? But what we require is 108. So we continue to the layer 2. We have down to a total of 25 feet. 5 feet of clay plus 20 feet of sand, right? And the nominal resistance up to layer 2 is equal to the nominal resistance contributed from layer 1 plus the contribution from layer 2. So in layer 2, the unit friction is 2.4 from our design chart multiplied with the thickness, total thickness, and which is 48 plus the previous resistance from layer 1. Total is 55 kips. We're still short, right? Because we require, again, is 108, which means that we need to drive the power further down, right? Then we go to the, before we get into layer 3, we could have maybe take advantage of the end bearing if maybe up to layer 2 plus the friction plus the end bearing, we could achieve that 108 kips. Why don't we check the end bearing before we tip into the layer 3? So at end bearing in layer 3, right, basically sitting on layer 3, and it's contribute as a total end bearing of 32 kips. So the total resistance nominal at this point is the friction plus 32, and you have 87 kips. But 87 kips still short, right? You still need to achieve at least 108 kips, which means that with the friction contribute from layer 1 and 2 plus the end bearing, it's still not sufficient to have that 108 kips. So which means that we need to drive the power further into layer 3. So, but we want to know how far we need to tip into the layer 3, right? So we can take the required capacity, which is 108, all right, minus the what we have up to this point, 87, and divided by the unit friction from the layer number 3. So in this arrangement, we could determine the penetration in layer 3 required so that we have a total resistance of 108. Yeah, are you following with this procedure up to this point? Okay. So let's say we need 8 feet, right? So 25 feet up to layer 2 plus additional 8 feet into layer 3, and total required depth of 33 feet. Questions? Okay. So let's check back the total capacity, right? So we have the resistance up to the layer 3 plus the friction that based on 8 feet penetration in layer 3, and the actual capacity we get is 109.4 kips, which is greater than what is required determined on the previous slides based on the Iowa design chart, 108. So we determined required penetration or embedded length of 33 feet plus 2 feet of embedment requirement for abutment, integral abutment into the power cap, plus 1 feet of cutoff. Also, so we need total length of 36 feet. Its norm here is that we usually route the power length to a nearest 5 feet increment. So at the end, we say that the contract length required is 35 feet, based on the calculation up to this point. Okay? So this is step 7. Right? You're able to determine the contract length. Next, we assume that this power is embedded in a non-cohesive or sand soil profile. Before even that we know the actual contract length or the embedded length. Right? Now we want to check back if the assumption that we made early is correct, because that will affect the selection of your resistance factors. Right? So now we have 32 feet of embedded length, minus out the 5 feet of clay, that gives you the total thickness in sand, divided by the total embedded length, and we have 84% of sand along the path, which is greater than 70%, which means that this pile is embedded in a sand or non-cohesive soil profile that is consistent with the assumption that we made early when we select the resistance from the resistance table. Right? So we can move on. If it's not, then you have to repeat the process again with the right resistance factors. Right? Go through the calculation, determine the length, and check back the assumption or the percentage. Right? The next is, in step 8, is to determine the target nominal driving resistance. We know that the power will go into that 35 feet into the ground. But we want to know that the power performance, and we want to verify that during the construction. So this step onward is to determine that parameter, the target driving resistance. We start out with this table. It's a table to show how we able to identify the right resistance factors with respect to the type of construction control as well as the soil type along the path. We know that in this example or in this project we use the Iowa DOT NR formulas. So we will limit the selection from the first row, and again the power is embedded in the non-cohesive materials. The resistance factors shall be 0.5. But note that there's a note here, F. Right? This table was developed primarily based on the steel pile historical data. But this foundation system is a timber pile. Right? So note F saying that reduce the resistance factors to 0.35 for redundant groups of driven timber piles. If the Iowa DOT formulas is used for construction, right? It's not 0.5, but 0.35 for construction control using the Iowa Blue Book, Iowa DOT ENR formula on timber pile. If it's a steel pile, then you use the number shown on the table, 0.5. It's a timber pile, we use a smaller resistance factors of 0.35. All right? But if this is to be controlled by BIP, for example, and the number shall be 0.4 instead of 0.5, right? Apply only for timber pile. So again, we want to find out what will be the nominal target driving resistance by rearrange the limit state equation. We have the same load factor load of 54 k's, but what is different right now is the resistance factors. Right? During the design, using Blue Book, we have a resistance factors of 0.5 that give us the contract length. Right? This one is to determine the target driving resistance, and the resistance factors should be selected from the table for construction control. Right? And the fee factors here is 0.35, and the target driving resistance shall be 154 kPa per power or 77 tons. Okay? If, for example, if you were to use WIP as your construction control, then you have a smaller target resistance. So what it means by target driving resistance is that during construction, you drive the pile, right? And the pile capacity shall equal or more than 77 tons at the end of driving. Okay? Although you may achieve that prior to the required embedded length, but we still continue to drive the pile down to the specified contract length. But most important that at the end of driving, that the capacity shall be greater or equal to the target driving resistance. Okay? Also, we want to, especially timber piles. Questions? Right.
It answered it. He answered it.
All right. For especially timber piles, we want to limit the driving energy applied on the timber pile, prevent the timber pile from damage. So in the interim bridge design specification, there's a criteria of a service load limit for timber pile 20 tons and a driving limit of 40 tons. Okay? And this 40 tons in the ASD or interim procedure has an embedded factor of safety of 4 in it. Right? So in the LFD design, everything is compared in terms of nominal. So what I did here is that it's not included in your worksheet. You may write down that the equivalent driving resistance or the driving limit for timber pile for LFD shall be equal to, you take the 40 tons, multiply with the factor of safety of 4, and divided by with the equivalent or the average load factors 1.45 and is 110 tons. Right? So we shall not drive the pile and exceed this capacity, which in other words, when you design and come up with a target driving resistance of 77 tons, make sure that what is required shall be smaller than the limit of driving of 110 tons. 1.4 is the average load factors. Right? It's actually shown on this that written by Mike. All right. So let's say we have a ratio of dead load to live load 3 to 2. Right? And in ASD, dead load plus live load is a ratio of 5. 3 plus 2 equals 5. But LFD, we have a load factor applied to the dead load and the live load. Okay? So you take the calculation, which is 7.25, and the average load factors, you take the ratio of 7.25 divided by 5, and that gives you the average load factors of 1.45. Right? For simplicity, because you have 1.25, 1.75, what I'm saying is that 1.45 multiplied to the total load, dead load and live load. Okay, that's where the numbers come from, 1.45. Any other questions up to this far? So we have, Ken.
But, you know, it's a reasonable way to go about it. It's just that we're still thinking about it. So just be advised that this may not be our final policy.
Would that be the same across, with this caveat there, is that the same across all pile types? Or just wood?
Just wood. Just wood, yes.
So then the LRTF then line those types of things for material type?
What's the question?
So this shows my ignorance of LRFD. So then those factors that you added or multiplied times the dead and the live load change for material type?
No, this is a load primarily from the superstructures on the pile. So the load factors will not change. It's not.
But,
we're
but
not
you've
changing-
not decided if you're going to use that 1.45 yet.
That's not. The issue here is the driving limit. How far do you go? We have a driving limit of, I guess, 160 blows per foot, just as a general driving limit. In the past, there's been a driving limit of 40 tons under allowable stress design for timber piles only. And we're still thinking about what that 40, because we don't know where it came from. And it's not a simple problem as to setting that number.
To add on on Ken's comment is that this 40 ton, if you refer to the current specification that show the design examples, that where the 40 tons show up. There's a statement below the 40 tons that these numbers is based on the past experience that observed by the IODOT on timber piles, that they feel that this 40 tons shall be a limit of the driving to prevent the damage on the timber pile. So, but we want to maintain that criteria as for now, so that we can use it in the LRFD. Of course, you may debate, shall it be a different numbers from 40 tons, but again, based on a past experience and a judgment need to be made there. In terms of equivalent values, and shall be 100 tons in the LRFD design.
Okay, there's another question. Let me just bring the microphone.
If you go to the slide for that talked about step 7, which talked about estimating the contract pile length. If you see the last sentence, which is round pile length to nearest 5 feet increment.
Right.
If I take 35 feet and deduct the 3 feet that is there because of the embedment of 2 feet and 1 foot of cutoff,
Right.
you get a pile length of 32 feet. And if I do the maths, you would actually end up with a
Smaller than
107 kips,
Yeah.
which is less than the 108.
Right. So you're talking about a difference about a few kips.
Yeah, but I mean, it depends. I mean, if I were to convey, say, 37 feet, then that would obviously be a bigger
So
difference.
what I'm saying is that you short by a few kips here because of you rounding it down.
Yeah, but in this particular example, that's fine. But it's an issue of if I come up with 37, then
Yeah,
do I-
37 you could round it up to 40.
Yeah, so I think we should probably go back and check to make sure how much of the difference is
Sure,
before
sure.
you make
That'll be
a
a
call.
good practice to go back and check.
Yeah,
In terms of the
just-
differences due to the rounding up of the pile length.
Right, just to
Right,
be
right.
know,
Good.
just to be safe, I guess.
Good note to make. Yeah. All right.
Any other questions? All right.
So you have determined the required information. Now is how you could put them on a plan and able to show the information to the site people and the contractors and whoever and read the plan and understand the design. All right. So this show the design notes will be a template is created in volume 4 for different structure cases, different template, different wording, and for different construction control. But this is particular template for design note for abutment piles. So I will read off from this slide the contract length of 35 feet that determined early. For the west abutment piles is based on a non-cohesive soil classification. Right? We know that the contract length is 35 feet. Is in a non-cohesive soil profile. A total factored axial load per piles PU of 54 kips. So we also include what is the factor load, design, used in the design, and a geotechnical resistance factors of 0.5. So a few important information is given here. Right? The nominal axial bearing resistance for construction control was determined from a non-cohesive soil classification and a geotechnical resistance factors of 0.35. So you have 0.5 for design and 0.35 for construction control. This is a good practice to put all this information on the plan, maybe like 5, 10 years later or 20 years later, somebody want to read back and understand the design. These are the important information shown on the plan, right? So of a replacement of bridges, you want to understand whether the foundation design early can be used for the new structures. These are the important information to have. The next one is most important for construction control and verifying the power performance during construction is that we have what we call the driving nodes. Again, shall be put on the construction plan. The required nominal axial bearing resistance for west abutment piles is 77 tons at the end of driving. So whoever read the plan, or contractors or inspectors or supervisors or engineers, they know that we need to achieve 77 tons at the end of driving. Okay? The contract length shall be driven as per plan unless piles reach a driving limit of 110 tons. Okay? Construction control requires a modified Iowa DOT formula. So it's specified on this plan or driving notes that what is the construction control method, what will be the target driving resistance that needed, right? And the driving limit for timber pile. So step 10 is the last step in the design office, is to cross-check the design and make sure that everything went as designed according to the using the right formulas, right factors, right specifications before producing the final plans for construction. Step 11 is the steps required in the field during the pile construction. Yes? Right.
The book shows 160 ton instead of
Right.
100.
Oh, sorry. That's a correction right there. 110. I forgot to highlight that. In fact, I highlight on the slides. Thank you for reminding me. Should be 110 as we calculate early. Okay? All right? So we want to select the right hammer that able to drive the pile, timber pile into the ground, as well as a hammer that do not overstress the timber pile. So in the Iowa DOT standard specification, table 2501-.03-1, there's a table to select the minimum energy required. In this case, it's a diesel hammer for the pile length and for the wood pile, as well as the maximum energy required. So we shall select a hammer that falls within this range. All right? So the minimum energy required, 17 kips foot, and the 24 as the maximum energy required, 24 kips foot. So if the contractor will provide you the hammer information, and you will have to check that if the hammer is appropriate for the construction of the timber pile. So you check if they exceed the minimum requirement of 17,000 pounds foot, or they do not exceed the maximum energy of 24,000 pound foot. So let's look at this. Dow MACD 19-42, setting number 1, the energy is 22,721 foot-pounds, which is greater than 17,000 and smaller than 24. is a right hammer to use. How about setting number 2 is exceeded the maximum required energy. And setting 3 as well as setting 4 exceeded the 24,000 foot-power maximum energy required. So in this case, we will accept the Dow Mac D19-42 at a fuel setting number 1. Okay. Again, you observe the construction. You record the driving resistance in terms of the blow count, the number of blows per foot or number of blows per inch, and resolve any construction issues. And this information, the hammer stroke and the number of blows, will be used in this dynamic formulas. This is an equation. The 12 is equal to the coefficient used in the current SD or interim LFD, multiplied with the factor of safety 4, that gives you the coefficient of 12. This is the new formulas, not totally new, but with the new coefficient that give you the determine the nominal resistance based on the field observation record of the hammer stroke and the blow count. Okay, so you have the set. Right, is the average power penetration in inches per blow for the last 10 blow at the end of driving, and this 12 equal to the conversion factor should be deleted. Is misleading. Is not correct here. This should be deleted. All right. So you have the set, you have the hammer information and the power information. You input the data into this formula and calculate your driving resistance. Right? This is a nominal resistance determined from the blow count. And we shall compare this with our target resistance that we calculate early, which is 77 tons. Right? We want to know at the end of driving if the power achieved the required driving resistance or performance. Okay? Although we drive it to the a contract length of 35 feet, but you may or may not achieve the target driving resistance. Right? So if this value is greater than the 77 tons of the target driving resistance, we will say that the power performance is accepted. If it's not, then we will do a restrike at 1 day, right? Retap the power, and verify if that new set determined at 1 day after end of driving, and input in this equation and calculate the new R, the driving resistance. If it's greater than, again, 77 tons, we consider the power performance is accepted. Again, if the retap driving resistance is smaller than the target resistance, you have two options, as what Don have mentioned earlier. Either you extend the power further down, or you perform a much complex analysis like using PDA, CAPWeb, or perform a static load test to verify the power capacity. All right? And that hopefully will able to solve the problem and achieve the power resistance with the options of driving further down or perform a more complex or more robust analysis. So to summarize this example, you have designed and identified the unit nominal resistance using the blue book. The resistance factors is based on the type of construction control methods that you select, as well as the soil profile, right? And the contract length is 35 feet. Construction control is again using modified Iowa DOT formula. Resistance factors is 0.35 for the construction control using the modified Iowa ENR formula on timber power. And the target driving resistance is 77 tons at end of driving, as well as at retap. That's all we need to verify the power performance at the site 77 tons. So hopefully by this example, you should be able to follow the design steps to come up with the contract length, to come up with the target driving resistance, and are able to select the right resistance factors for design as well as for construction from the table. So with that, I would like to open for questions if you may have.
Questions?
Yes, Mike.
All right.
Probably maybe more of a comment. I don't know. Two things. I think that 12 might actually be a conversion factor because if you look, the energy was in foot tons and the S below was in inches per blow. So, second comment.
Depending on the unit you put in.
Yeah. Second comment, particularly about timber piles, is if you think about it, for those of you familiar with our interim procedure, the fee factor is 0.725, and that's kind of used in design for the contract length and also what we sort of use to put on the plans for the capacity. But now we're saying the fee factor for the target driving resistance is 0.35, which is significantly lower. So I think it's a possibility you may find the contract length might not be long enough since that was based on a 0.5 in the design. So I would have just a little concern. We don't drive a lot of timber pile for the state, but it's something to watch out for. So I would just say that, I guess.
And this might address Mike's thing, because on step 6 you're dealing with 108 kips. That's what we need, except
That's what you need to determine the contract length. It's not the numbers that you need to verify the power performance at the site. It's the number that you need to calculate to able to use in the step 7 to determine the contract length needed. All right?
but they're not the same, and I'm not clicking why that is yet.
All right. You see
Unless
that
it's the funny factors there that they're.
Right. Obviously, they are not the same, right? Because of the methodology used in design the power and the methodology in verifying the power capacity. Right? You design using Blue Book. We know that Blue Book is the most efficient method. Right? It's a good method that we're confident about it. We can design using Blue Book with fee factors of 0.5. But in this timber power, it's 0.35. 0.5 for design. But when you verify the power capacity at the site, you're using a method is the dynamic formulas. We know that dynamic formulas is conservative, has a lot of uncertainties, and the accuracy is not as good as other methods. That it bounds to give you maybe overestimate or underestimate the actual capacity if you were to test it with load test. For that reason, we have a different resistance factors that were used for the Iowa ENR formula. And for that reason, we will have a different target resistance from what you have in the design of 108 kips. All right?
It's good. That makes sense? Okay. Any other questions?
I think the confusion is you're calculating pile length using both methods. And I think kind of what Mike's saying, if you use 0.35 for the original calculated length, won't you come up short then? Would you want to consider, I think that's where the confusion is.
No, okay. Let me clear out. For design is 0.5 using the Blue Book, right? for design and come up with the contract length. That's the three factors we use, 0.5, right, to come up with the contract length. But because of the method for verifying the power capacity is different, we will have a different three factors for that to determine the target driving resistance. What I'm saying is that the three factors for construction control using the Iowa ENR formula is 0.35 for timber power. All right, so 0.5 for design, 3.5 for determining the target driving resistance. Two different items here. All right?
So,
Because you're going to have two different resistance for design and the resistance determined at the site using the dynamic formula.
so Dean is a structural engineer, and so those of you who are structural engineer, I'm a structural engineer, so let me try to address it differently. So unlike what we typically do for structures, here, depending on the method you choose, your capacity changes. So we are using a blue book for the design because that's what's, as Cam said, found to be the most efficient. So you get one value. If you turn around and use a different method, you get a different capacity. So because you get different capacity for the same problem, when we back calculate a resistance factor, they vary various numbers. So the 0.5 doesn't mean that that's the most efficient method. Sometimes 0.35 could give you a higher value because you end up with a higher capacity when you calculate the capacity based on the dynamic formula. So they're not the same numbers. So to resolve those issues, what we have done is we actually used efficiency for different methods, which accounts for the the capacity as well as the resistance factors. And in terms of deciding which method is most appropriate for Iowa, it was all based on the efficiency rather than the actual resistance factors.